So if you have a leveled laser scanner in a particular place, it's going to be leveled. You know that there's going to be leveled with respect to the gravity, okay? This by itself would provide the opportunity for us to identify what the floor and the ceiling is going to be. Why? Because for a, let's say, a room like this that is going to have a floor and a ceiling, if you take a look at the histogram of point height, there's going to be two peaks. One is going to be on the floor and one is going to be on the ceiling. If you move it into that direction, you're going to have a lot of points on the floor and a lot of points on the ceiling without change or significant change in its height, right? Why? Because you have, what is the points on the floor? Points on the floor are the points that have the same height, right? Because they're all on one floor, right? And the deviation that you see here is basically the random measurement error that you're going to be seeing going up and down for that particular point. But they are going to be similar to the normal distribution. They're going to basically distribute themselves around a median, right? So you have these points on the floor, these points on the ceiling. Now I can identify all of these points from the floor and the ceiling only using the height. So one dimension. I can gather all of this information and all of this information. And you see from these, this part and this part are much more than all of the rest, right? So in many cases, for instance, in rooms or especially on construction site when you don't have, let's say, envelope walls yet still built, you just have skeletons, really the majority of the points that you're going to be having is the floor and the ceiling. And next semester in the field information modeling, you're going to be seeing this very clearly using the point cloud data that I will provide to you. That if you just have these columns and you floor and the ceiling, the majority of the points is the floor and the ceiling. So because of that, and because of the fact that we are removing, let's say 80 to 90% of the points at every time, using only one dimension versus the three dimension, if we want to compare it, that would be around 15 to 25 times different in terms of its computation. This means that if it's taking 1 day versus 15 days, you see, it's huge. Just by simply defining the problem, changing the parameters, and thinking about it a bit more creatively by reducing the problem's dimensionality. One of the methods that I proposed there was a simple method to be able to detect large planes from point clouds. So for something like this, what we do is we typically have to first identify what neighborhood around each point we want to use. So these neighborhoods would be utilized in order for us to extract curvature information. So for this, we extract planar surface information. For that, we need the normal vector of that. So that is the easiest way to be able to detect large planar surfaces. We find the normal vector. So the normal vector of that is eigenvalue decomposition of the covariance matrix of that. And you find the smallest eigenvalue for that. The eigenvector that corresponds to that smallest eigenvalue would give you the normal vector. So the normal vector, once you get it, how these types of objects are detected and how I have proposed to detect these types of objects, the majority of the normal vectors are directing to. So you have this plane and this plane here. For planes that are separated, the normal vector is still in the same direction. Okay, what that means is if you have two planes here and two planes here, our expectancy is that the normal vectors are directed in either this or in this, right? So this is why and how we are able to do that. What we do is we take the distribution of our normal vectors out. We go and we find where the mode of these normal vectors are. We first go with the larger one, and we find where the normal vector is. What I do is I rotate it so that the z-axis is parallel to the direction of that norm. What it looks like is something like this, meaning that now if I do that normal vector towards the direction of the top, our sides here are going to be represented by these two, if we just look at it in terms of its height. Once we do that, and this is basically where the normal vector is going to direct. And then here is going to be a majority, and here is going to be a majority. Why? Because all these surfaces around here have no points associated with that, okay? Once we have that, then we also again have to detect the mode here. And then once we detect the mode, we get the points around that mode. And then we perform a robust plane fitting that I've proposed in that basically manuscript there. And from that, we get that and we detect these. So this is an automated process. It's very simple, easy to follow. Let's take a look at, as my final thoughts today in this session, on how it compares to recap. The planes that we originally detected using recap manually, which I had to select 3 points, and doing that, my method takes approximately even less time than that, and it hasn't even been optimized for for speed. So these are the original planes. I'm going to basically take a look at 2 planes, and these are what I have detected using my method. If we take a look at this plane, for instance, if we go and zoom in, we're going to see that my method, which is the yellow one, did not detect all of these other basically outside of these realms that the manual method that we had proposed there had actually done. And I think I changed this to white so that we can have a better view of that. And you see, even on the bottom there, all of those other ones are from the manual method that we've detected. So all of these points that do not belong to that plane in the manual basically method that we went through today in this lecture, we see that it's significantly different. And that was an automated method, very simple method to implement. And you can utilize that and extract the information that you want from it as accurately as possible.